Okay, let's dive right into this explainer. Today, we're building our physics foundation by looking at exactly how we measure the physical world. I mean, whether you're building a massive skyscraper or studying something in the subatomic realm, physics demands absolute precision. We can't just guess, right? We need standardized ways to quantify what we see, feel, and experience. So, let's unpack the essential physical quantities and the measurement techniques that literally let us decode the universe.
Here is our roadmap for today. First up, measuring length and volume. Then, we'll look at timing and averages. After that, we'll tackle scalars versus vectors, and finally, calculating resultant vectors.
All right, Section 1, measuring length and volume.
Everyday lengths, from a few millimeters up to a meter, those are handled easily with a standard rule or, if you need more precision, some calipers. But what if I ask you to measure the exact thickness of a single sheet of A4 paper? Your standard ruler just isn't going to cut it. So physicists use a really clever workaround. You measure a large multiple. Think about taking a pack of 500 sheets of paper. If you measure that whole stack and find it's 49 millimeters thick, will you just divide 49 by 500? Bam! You find that a single sheet is 0.098 millimeters thick. It's such a simple, elegant solution to a really common problem.
Now, transitioning from one dimension to three, let's talk about volume. Finding the volume of a perfectly rectangular block is incredibly straightforward, right? You just measure the length, the width, and the height, and multiply them together. But the physical world isn't just made of neat little boxes. We absolutely need a different approach for things like liquids and irregularly shaped solid objects.
So when you're using a measuring cylinder for liquids, you have to account for the physical properties of the liquid itself. Take water, for instance. It has surface tension, which actually causes its surface to curve downwards in a cylinder. We call that curve a meniscus. To get an accurate reading, you literally have to get your eye horizontally level with the scale and read the value at the very bottom of that meniscus curve. If you look at it from an oblique angle, like looking down from above, you introduce what's called parallax error, and your data is instantly flawed.
And this brings us to the displacement method, famously discovered by the ancient Greek mathematician Archimedes. It's brilliant. It beautifully solves the problem of measuring irregularly shaped solids, like a rock or a weirdly shaped lump of metal. You just note the starting volume of a liquid in a cylinder, carefully lower the object in until it's totally immersed, and watch the water level rise. Because the object pushes the water out of the way, that increase in the volume reading, that is exactly equal to the volume of the object itself.
Moving right along, Section 2, timing and averages.
In physics, we're constantly using clocks and digital timers to track events. But consider this for a second. How do you accurately measure the exact time of a single rapid pendulum swing? We call that its period. Just think about the mechanics of you standing there holding a stopwatch. You see the pendulum swing, your brain has to process that visual, send a signal down your arm to your finger, and then you press the button. That human reaction time introduces a massive percentage of error when the event you're timing only lasts a fraction of a second. A single short interval is just way too quick to measure perfectly. So how do we fix that?
Well, the crucial point here is that we borrow the exact same logic we use for that single sheet of paper. By using a stopwatch to measure a large number of multiples, say timing 20 or even 50 complete oscillations, and then dividing that total time by the number of swings, we drastically reduce our human reaction error. That fraction of a second you were late hitting the button, it's now spread out and diluted over 50 swings, which makes it statistically insignificant.
Check out this data from a pendulum experiment. The students didn't even try to measure a single oscillation outright. By timing 20 swings first, they could calculate the precise period of a single oscillation with a really high degree of accuracy. I mean, they calculated it out to 3 decimal places, like 0.905 seconds for the 0.20 meter string. It just goes to show how absolutely crucial methodology is for accurate data collection.
Okay, Section 3, scalars versus vectors. In physics, we divide quantities into two primary camps, scalars and vectors. A scalar quantity has magnitude only, and magnitude just means size or amount. A vector quantity, on the other hand, has both magnitude and a specific direction. That is the key difference, and it completely alters the math. Think of it this way. If you take a rambling 8-kilometer walk through a forest, turning left, turning right, doubling back, your total distance traveled is 8 kilometers. That's a scalar. But your displacement, your exact straight-line position from where you started to where you finished, which might only be 2 kilometers north, that is a vector.
There's a great quote from the source material that hits the nail on the head. A force of 3.0 newtons upwards makes sense, but a temperature of 47 degrees Celsius sideways does not. You just can't assign a direction to everything. A force pushing upwards paints a crystal clear physical picture, but a temperature sideways? That's complete nonsense. And that fundamental truth is exactly why we must rigorously separate scalars from vectors.
So, let's lock in the essentials. These are the specific scalar quantities you need to know: distance, speed, time, mass, energy, and temperature. The main thing you've got to remember about scalars is that they only ever add up to a larger value. If you have a 2 kilogram mass and a 3 kilogram mass, you have 5 kilograms. Because they have no direction, there's literally no way for them to counteract or cancel each other out. Now, here are the essential vectors. Force, which by the way includes weight, since weight is just a gravitational force acting downwards, velocity, acceleration, momentum, electric field strength, and gravitational field strength. The fact that these have direction completely changes the game when you add them together. Their directional arrows can reinforce each other, sure, but if they're pointing in opposite ways, they can push against and completely cancel each other out.
Which leads perfectly into Section 4, calculating resultant vectors.
Imagine you have an object, and two different forces are acting on it at the exact same time. When you have two vectors acting at right angles to one another, like, say, a 2 Newton force pushing up and a 4 Newton force pushing right, the object isn't just going to move straight up or straight right. It's going to be pushed in a diagonal direction. We need to find the overall combined effect of these forces. In physics, we call that combined effect the resultant vector.
For vectors at right angles, you can actually determine this resultant graphically without even needing complex trigonometry. You start by drawing the two perpendicular vectors accurately to scale, let's say 1 centimeter for every newton. Then, you use those lines to basically complete a visual rectangle on your paper. Finally, you draw a diagonal line straight from the origin point to the opposite corner of that rectangle. The length of that diagonal line, when you measure it with your ruler, represents the magnitude of the resultant vector. And its angle, that gives you the exact direction the object will travel.
And that brings us full circle. We started with a simple ruler measuring a piece of paper, and we've ended up diagramming invisible forces that dictate how the universe moves. Actually, I want you to look around you right now. Gravity is pulling you down, that's a vector. The chair you're sitting in is pushing up against you with an equal and opposite force, another vector. The temperature in the room is a scalar, interacting with your body's energy. If vectors and physical quantities dictate the exact resulting movement of absolutely everything, how are all those unseen forces balancing out in the room you're sitting in right now to keep you perfectly still? I'll leave you with that thought to spark your curiosity about the invisible, highly measurable forces holding our physical world together. Thanks for joining me on this explainer. Keep questioning and keep measuring.